Okay. Hello and welcome to another wonderful adventure of the New York City Category Theory Seminar. Tonight we have Florian. I guess I can call you one of my oldest friends
Yes,
from I don't know. When did you come to the Graduate Center first? 96, 90, no, before 95, 94,
95.
95.
Then
Since
it's 95.
1995, Florian Lengyel, who has to do with the City University, and he's a good friend and a good mathematician, as you will see in a minute. And he's going to talk about the geometry and combinatorics of diagonal simplicial tensor modules. Take it away, Florian.
Okay. Let me let me start here. Um, this came about through some computer experiments uh, modeling simplicial objects with simplices that are tensors. So you could think of these as simplices with additional parameters. And as I was experimenting with these, with horn filling, which we'll get to, uh, I found a way to construct n hypergroupoids to build generators of these things on the computer and algorithmically, I should say. And I think the concrete computations of these things disqualifies me in category theory. Is that not correct?
By far, that's it. You're kicked out.
Yes, I'm out.
Hmm.
So what I'll describe is a functor, the diagonal simplicial tensor module, which depends on what's known as a shape, at least in computing, a set of parameters for the axes, in this case, k-axes. That's the order of the tensor. And I'm going to define the simplicial dimension as the minimum of those parameters minus one. Okay, so there's a reason for that. What I'm giving you, given those parameters, is the top dimension beyond which all the tensors are going to be degenerate. They'll lie in the degenerate submodule of the simplicial tensor module. And at each degree P, dimension P, those
Florian,
are,
can we back up for a minute?
yeah,
Okay, so I know what a simplicial set is. Okay,
right.
so
Well, I'll get to
so
that.
no, so what are you talking about here? First of all, it's the tensor module is a module over some ring,
Yeah,
or
right, over ring AL, I should say. The ring is just any commutative ring.
okay, and I know what a module over ring is. What's a tensor module?
Okay, here I will I'll have to say then I have to get to the construction, which is that I have to define certain boxes, certain sets, and then I'm going to take the cotensor on this set and essentially hypermatrices. That's what I mean by a tensor. It's arrays of numbers.
Okay. So
Uh,
hyper matrices
right,
are
higher dimensional numbers.
multi-dimensional arrays of
That's
numbers.
right.
So that's what we're dealing with.
That's what we're dealing with.
Okay.
And that's what we're dealing with. And the what we do with
So
the
so
minimum
so one
rate,
second. So X is going to be such a thing,
that's right.
and P is telling you its dimensions,
That's
or
right.
P is which dimension it is. Okay.
Right. So
And
N is telling you the top dimension uh, such that every other for all dimensions higher than that, that's the top dimension where you have non-degenerate simplices, non-degenerate tensors. Okay, so everything else above that lands in the degenerate submodule. but I'll say what that is. In this subject, you have a degenerate submodule, right, which is generated by the images of the degeneracies. So it's easier with ordinary simplicial sets, but with this, you have to be careful about the degenerate submodule. Okay, so what I want to do is define within this simplicial object, this module. Uh,
Florian, by the shape, you mean what the dimensions are in each
right,
layer?
that's right. These are the axes. Okay, so N1 is one axis. So, for example, 2, 2 would be a 2 by 2 matrix. Okay,
Okay.
okay.
And,
So
and
let's go to examples then. All right, so here's shape 3, 3. The simplicial dimension is 2. Okay, and here are the face maps. So if I knock out row 0, excuse me, I move my cursor along the column. uh, Row 0 and column 0, I get this. Okay, x11, x12. If I knock out the middle, right, x11, I get x00, x02, and so on, and so on. So those are the face maps, and they're defined by precomposition. There's the diagonal. It's precomposition by the coface maps. Okay. Now I'm allowed any parameters, so there I have to take the minimum, and so my subscripts I only go from 0 to the dimension. Okay, so here I have in dimension 2, I have a 3 by 3 matrix. I could have a 3 by, I don't know, Google matrix, but the dimension still would be 2 here. And then you would go down the, what I'm going to call the principal diagonal. Okay.
So if n equals 3, you'd be coming in and out of the page.
Uh, right. Well, if k is 3, I'll come in.
Yeah, yeah.
Yeah, if k is 3. This is what it's going to do to I'm sorry, these are what the codegeneracies do, or the degeneracies. They duplicate in both of the axes. Okay. So here you get a colored diagram, which is okay, so let's look at the 0th degeneracy. So that is going to duplicate the 0th row and column. So down here, I've made them red and blue, and those are purple. So not that that matters. You can see what happens for S1. In case these are a little unfamiliar, we're going to duplicate the first row and column, and so that's what you get. They get expanded, if you like. Okay, like that. All right.
okay, so in general, simplicial sets have degeneracy. They somehow describe topological spaces because they have degeneracies and codegeneracies. And now
Yeah.
you're saying not only do they have it, but multidimensional matrices have the same type of structure.
That's right. That's right. There are many ways. There are different ways to do this, but this particular one will give you a model of a certain kind of higher category. That's infinity category. I mean, it's true that I'm going to get lifts of horns for every index, whereas in the general case, you only care about inner horns, but that you have. You don't want to see I guess you don't want to see the the definition. So anyway, right. The point of this is right. There's a realization joint to the singular functor, I guess. There's also Quillen's result, which says something about the homotopy theories of simplicial sets, same as that of topological spaces, actually compactly, what is it? Compactly generated weak Hausdorff, if I'm not mistaken. That's the equivalence. That's an important theorem. Uh, that's, but you need degeneracies for all of that to go through. So here's the object. Here's the definition, but when you have modules, you have to think about the degenerate submodule. I keep saying that. You have base change for this, change of base. That's because the cotensor is with a finite set. Gives you a finite free module on the ring A as an A module. So we don't have to see that. So let me just say what a horn is. So there is a standard simplex. Okay, should I go back and say that's the representable functor on the ordinal n? But that's a subcomplex of this representable functor, a simplicial set by unatives. What we mean is that an ordered collection of elements. Ordering is important. You can have two 4x4 matrices with exactly the same set of principal submatrices, and so they can't be distinguished if you don't know the order in which the phases occur of the horn. Okay, that's a result of Manville and Stockmeyer of 1971. Just saying. Okay. So a filler is an element that will satisfy these equations. And we'll give you something at J, index J. This is the NJ horn, by the way. And that corresponds to a lift of the horn. I don't have the full triangular diagram here. And to the representable functor. And what this is going to do, what this means is that we're going to send this identity of the representable functor, right? It's a Hom set to the element T, and that's going to generate a submodule, a simplicial submodule. That will be important later because we want to discuss the moduli spaces of these things. Anyway,
Florian, a submodule would be a hypermatrix of the same size, but in what sense is a submodule?
Well, at each degree, you're going to generate a module, and then by applying the degeneracies and face maps everywhere, you'll get a simplicial object.
I understand, but the numbers will be the same inside the hypermatrix?
Yeah, well, you get right. What you're going to get, which numbers do you mean? Do you mean the numbers? Let's go back. You're going to get, as you apply a face map, all of these, the K is going to stay the same, but these will drop, right? They'll drop by 1. Okay. And as you apply a degeneracy, they'll increase by 1. So, but we're starting at this dimension n if we're going to generate a module, a simplicial tensor module from a tensor of dimension n in this sense.
But a subtensor module will have the same shape.
Yeah, that's right.
and it'll have the
8
same
degrees.
dimensions along the way. The
Yes.
only thing is, it's going to, in what sense is it sub?
Oh, well, in the sense that uh, it will just have, see, this one is the full, the x dot is the uh, full function space, if you like, full, all the, it's actually the, what, a linear, excuse me, dual of the free module on the set S. So it's a finite free module because that's not that S, but um, on the indices. Okay, so in what sense is it? Because each one is a submodule, a generated submodule of the full space of maps out of the index sets. Okay, and the face and degeneracy maps commute with the well, they do what they're supposed to do.
Yeah, I'm just trying to understand in terms of a hypermatrix, you have numbers inside of
Right,
the hypermatrix. And I
right.
just want to know, are the numbers different in a sub tensor module? The
Uh,
entries in the hypermatrix, is that different?
uh, they well, no, not for the generated one. The entries are going to be those you get by adding the generator. Right? You can
Okay.
get right or multiplying it by scalars. You can do that. It's just an ordinary module. Oh, sorry about it. This was just something else I did. It's by the way, it's not really germane. It's just that one thing about the simplicial homotopy, the contraction to the zero vertex, is a cute way of seeing it, which is just to multiply simplices. So you often see funny diagrams with hand waving diagrams, but this is not a hand waving. Anyway, let's see. Let's try to make sense of a horn. Okay, so um, if you knock out, we'll start with this. We'll start with this one. So if you consider the one horn, it's got D0 and D2. Okay, we'll go back. And the so what will what happens is back up a bit. Um, simplicial uh, simplicial modules are the cant vibrations right there. All horns have fillers. You can always do this. There's an algorithm, a procedure for doing it. And so if you take the difference, you'll notice if you take the difference between the original tensor we started with and this filler, what you find is that, well, all of these are zero, of course, and you'll find the support is on the indexes 0, 2, and 2, 0. Okay. And one way to look at that is to think of the horn kernel. So the horn kernel is you say, okay, D0 is 0. That's D0 there. You set that equal to 0. And and this has to be set to 0. So all you're left with are essentially coordinate tensors with a 1 here at 2, 0, or a 1 at 0, 2. And that's almost the entire story, except except that we have to say something about the how the horn kernel is generated. In some sense, that's almost the whole story right there. So I'm just going to say there's an exact sequence, this horn kernel. I tried to indicate it using that example. And
I'm sorry, Florian. Are you saying that these hyper matrices do they form a a battle category?
no, well, I suppose I haven't gotten. Well, okay, there is a simplicial homotopy theory for them because they are Kant complexes. Yeah, that's true.
Okay, and when you look at the homotopy category, is it equivalent to the homotopy category of simplicial sets and of topological spaces?
The whole thing.
Yeah.
Good question. I'll have to get back to you. Uh,
Hmm.
I that's not the direction I'm going here with this. This is more algebraic combinatorics and uh, that I can't answer the question now.
Okay, okay.
I uncle. Okay,
Mhm.
so all right. So we just have an exact sequence here um, with the horn kernel. Okay. Uh, the the set of fillers is a torsor, and they're unique if and only if the horn kernel is zero. This is true for every J, by the way. It's independent of the index. I have to say something about normalization, um, uh, about the Dold-Kent correspondence. Just because the horn kernel is going to be isomorphic, is isomorphic to the normalized complex. Okay, so there's the relevance of all of this is that there's a direct sum decomposition of this. This holds for anything, any um, simplicial module. But and I mentioned the degenerate submodule. It's this sum of images of the degeneracies, right? And so there is a direct sum decomposition, so that gives you a complement of the degenerate submodule. And so I'm going to have to prove something. I do prove something. It's in the preprint. Uh, that the horn kernel is also a complement. So it's isomorphic to the normalized complex. Okay, so the the the, the so we'll be able to compute the rank of this. Um, so we have to define an algebraic n hypergroupoid. So that this is again, this is the usual setup. Um, Essentially, in dimension, in our case, it's going to be true that horns have unique lifts above dimension n, and they're not going to be unique from dimension one through n. Okay, that's the statement. That's what this slide comes down to. And this is all borne out by computation. um, so so what I'm going to show is before there was a certain set of indices, right, that were missing from the horn, right, 0220. That's going to be the case generally, and the what you have is a support characterization theorem, which says that the Horn kernel is the free module spanned by the, well, I say the missing indices, but what I really mean is the coordinate tensors at the missing indices. Okay. And then there's a Horn non-degeneracy lemma, which says that that the Horn kernel, any one of the Horn kernels, is a complement of the degenerate submodule. And so that the Moore construction guarantees the existence of degenerate fillers. And so if you start with a non-degenerate tensor and then you compute a filler, the difference tensor is non-degenerate. And then combining these, in this special case, because because you have a complement and they're both you can use the isomorphism theorems to get the Horn kernel is isomorphic to the normalized submodule. Anyway, I don't know how much more want to do this. So the index is missing if it's not in the image of the product of the face maps. So there's a combinatorial characterization of this. It's really just logic. So you want to say that an index, a multi-index, is missing from the NJ horn if and only if the image, in other words, all of the elements of the index is contained in this set, all the elements except J. Okay, so maybe I'll skip through this. The point is that the Horn kernel is a free A module with this basis. Really, it was more exciting when I was calculating on the with algorithms. Okay. So anyway, the point is that the Horn kernel, there's a precise point. As long as the number of axes is equal to or exceeds the what I call the simplicial dimension, then the Horn kernel is not zero. Okay, and here are the rank formulas. This is from exclusion exclusion. Okay, to calculate the set of missing indices, and in the constant case, and that case will give you a hypergroupoid, n hypergroupoid. In this setup, you get essentially the count of what is it, surjections. Okay, and so here are some ranks, if you like.
Florian, I don't know if it's me, but your thing is not centered. Is that me? Or is that only me?
Not centered, or what? Am I? Maybe my head is
No,
not.
maybe I did it.
The
Is
slide is
every
good for me.
Yeah, the slides are good. I'm sorry. Okay,
Okay.
go.
As long as it's a slideshow, that's
Fine by me.
Okay, sorry. Go. Sorry.
okay. So I mean, here are some shapes. I mean, uh, I'm sorry. For the constant shape, you'll see. You'll see, for example, let's see. So dimension 2, k equal 2, n equal 2. Oh, it's a 3 by 3 matrix. So the order 2, n equal 2 corresponds to the 3 by 3 matrix that we had. We just there were 2 missing indices and so on. You can vary these, and you might find a sequence not in the online encyclopedia of integer sequences. I kind of doubt it, but this is what it looks like. And now here's the issue. We've been speaking about this big ambient simplicial module of big multi-dimensional tensors, right? And possibly. And I did my calculations just with individual tensors. So uh, under what conditions will I get the full ranks? That's what I want to know. So so I had to define, this took a while. I had to define what I mean by a generic tensor. So for that, I mean that the difference between the tensor you have and the filler that the Moore's algorithm gives you has maximal support. In other words, it's exactly the set of missing indices. So that will work in the numeric and the algebraic, you know, in the polynomial case as well, where you have indeterminates. So the first fact is that the set of generic tensors is a non-empty Zariski open subset of the nth degree piece. And let me see what else. Oh yeah, I've learned non-degeneracy. I'm not sure if I need to say that. Oh, okay. We'll skip to the hypergroupoid threshold theorem. The simplicial module is an algebraic n hypergroupoid if and only if k equals n. Okay. So I may just decide to skip the proof unless you want to see it. I think. Hope you like my background, but it's completely fake. All right.
Okay, go talk.
Okay.
Sorry.
No, not at all. If anyone should be sorry, it's me. All right. Okay. Here we are. Now I somehow have the inability, I'm not able to manipulate my slides. So let's go.
Oh, so maybe I have to make you a co-host. Sorry.
No, it's okay. I can do it.
No, you are a co-host.
I am a co-host. All right. Let me see if I can reduce this. There we go. There were too many. I don't want to see the participants. I want to pretend I'm talking to myself. I mean, I do that anyway. So there's the hypergroupoid theorem. That's when things went south, and with Zoom, and there is the whole. I think when you left, I mentioned that the diagonal simplicial tensor module, this whole family of them, depending on the parameters, it's contractible. It's acyclic, and there's an explicit homotopy. I guess the nice thing about that is that it's all constructive, which usually in homological algebra you have non-constructive resolutions. I mean, okay, it's the resolution of the zero module, but you know, it's still a resolution. So here is the homotopy. Okay, the shift and truncate. And then I just want to mention with oh yes, then there's stable. Okay, it's equivariant under the stabilizer. If we look at the constant shape, then this is for the recording. The face, degeneracy, and boundary, and I guess the homotopy too, preserves subspace is preserved by this action. So for matrices, they preserve symmetric matrices alternating. In the case of the complex numbers, Hermitian forms, Hermitian matrices. So this was right. What I said was this was wrong. The tensors is wrong. Oh, look at that. You see everything. Here we go. Here we go. And Hermitian forms, and for number fields with an involution, these maps will preserve the involution also. So anyway, those are also give you contractible simplicial submodules. I think I will skip this. This is the spectral sequence collapse. That's to the E1 page. Okay, but I'll skip that. Now, if you want some homology, the dichotomy there is that K has to be at least n+1. Okay. So there are a couple, so you'll get, you won't have homology in the big complex, but you will get non-zero cycles, I should say. All right, so next, I think I mentioned that I was working with individual hypermatrices, tensors, rather than the full ambient module, the full diagonal simplicial tensor module. And so the question is, to what extent are these generic? So I think what I want to do here, how do I want to explain this? Okay. So here, in this case, we work over a field, and there's a map from the this is a simplicial map, by the way. This is the simplicial object, simplicial module generated by the standard simplex, and we send the identity of this to the tensor T. And so the image of this is a generated submodule. Okay. And that map, I call it F sub T, has a kernel, and if you mod out by the kernel, then there's an isomorphism class of this, and in each degree you have a kernel really in each degree. So you want to I wanted to know the generic behavior of this. So so there is such a thing as the generic rank. I have to explain that. And that's going to be less than the rank of something called a collision map. Okay. Okay, so essentially what you want to know is where do I get something that looks like the standard simplex? that's what you want to know. And so in order to do that, you parameterize the points by Grassmannian, by a product of Grassmannians. And so there's a locus where the kernel sequence, you could call it, achieves this generic rank. And so there's a moduli space of kernel sequences. You know what? I'm almost out of time, I think. I'll just try to give an example. Okay. So if we look if we look, say, at we'll take dimension. No, you know what? I'm going to I think what I want to do is stop.
Okay, okay.
I'm not going to be able to just say what I want, and I don't have enough time to do that. I apologize for that.
It's okay. Thank you for a wonderful talk, Florian. Okay. Any questions? Any discussion? Go.
I was just curious about the, origin or motivations of this. I mean, why to try to construct simplicial sets out of tensors?
Oh, well, it was to construct n hypergroupoids.
Mm-hmm. Okay.
Yeah, I mean, it became apparent that as you vary the dimensions of these things, the number of axes as well, the order and the dimension, you would get you'll get n hypergroupoids. Those are n types, homotopy types, explicit realizations, and you can do this on a PC. I mean, you won't get the full infinite object on the PC, obviously, but you'll get a generator.
Okay.
Florian, why is it a groupoid? In other words, not every matrix is invertible, and I'm sure not every hypermatrix is invertible. So why is it a groupoid, not just a hypercategory?
It's a hypergroupoid. This is the Duskin-Glenn definition, right, which says that there are lifts above. The lifts are unique above dimension n, but non-unique at dimension n. Okay.
So it has nothing to do with matrix multiplication, or
Right, that's right.
Okay, so composition, composition of maps is what? In other words, if you're going to have a hypergroupoid, you have to have some type of composition.
Right. Because I mean, isn't it group? Because I was just expecting you said groupoid.
No, it's a
Is it
simplicial
groupoid
set.
because of the horns are being all filled makes it a group, makes invertible in that sense?
Well, it's a simplicial set, right? So if the horns fill up uniquely, then well, that's what that.
Yeah.
That just means the composition is on the nose, and it's not so below the dimension n, right? Defined up to homotopies.
All right, Florian, what do you want to do next, other than answer the questions about homotopy theory?
What do I want to do next?
With this?
Oh, with this? Well, I suppose that's a good question. What I'd like to do is do this for group in groups rather than and simplicial groups rather than simplicial modules. That's what I think I'd like to do, if it's possible.
I understand.
Yeah, because all this is going to give you is Eilenberg-Moore spaces, right? That's what you'll get. You won't get anything more than that.
Yeah.
So,
Anyways, let's say any other questions? I think we should thank our speaker. If you want to learn more about model categories and homotopy, next week Emilio is speaking, and he's going to he's going to start at 6 and give an earlier talk on what model categories are all about, and then his real talk will be at 7. It'll be an in-person talk. Anyways, and Florian, you're going to give me the final version of the slides. You're going to send me afterwards. You're going to make some changes and then send me and then I'll put it up tonight.
Yeah. And also, I'll finish my notes. So
sounds good. All right, ladies and gentlemen, it's a pleasure. Have a wonderful evening. Take care.
Thank you, Florian.
Okay.
Thank you, Florian.
Thank you. Glad to hear you again.
Thank you.
Thanks for having me at the New York category theory.
Sounds good. Florian, thank you. Stay in touch, Florian.
Okay.
Take care.
Bye.